So we are going to look at our next example here. Similar idea, but a little different twist. So in example 2 here, we are going to find the volume of the solid obtained by rotating the region. That's usually how all of these problems start, by the way. Say, find the volume of the solid obtained by rotating something, blah, blah, blah. So our region here is bounded by y equals x squared, x equals 0, and y equals 4, and we're going to rotate that about the y-axis. Okay, so you can see it's similar equations to the last one. We're going to be using that same parabola, but changing some of the other boundaries a little bit. So let's graph this. Okay. Set up your axes. Okay, so y equals x squared, of course, that's our parabola again. There we go. And then we have x equals 0, which is the y-axis. So the y-axis is one of our boundaries right along here. Okay. And then our other boundary is y equals 4. So that would be the horizontal line right here. Okay, so that's y equals 4 right there. Oops, just got rid of the axis. Okay, y equals 4 there. Okay. So, yeah, we are just looking at the area that's bounded by those 3 curves. So that's going to be this area right in here. And we're going to take that area and we're going to rotate it about the y-axis this time. So we're rotating like this. So you got to imagine that area there coming out of the screen, wrapping around, curving around. I'm making the little motion in the air for me, but I know you guys can't see that. It's going to hit your screen again over here. Kind of making a little shadow image over there. And then it's going to continue behind the screen and sweep around that way until it's come around full circle. So I'm going to attempt to draw our solid again. And this is a solid, right? There's no holes in this. Before I try to sketch it, what do you guys think this is going to look like? What type of shape is this going to be? Yeah, Brandon thinks it looks kind of like a bowl type of shape. Yeah, like a solid filled in bowl. Yeah, cool. Yeah, so that's the idea there, like a bowl or a top of a wine glass or something like that. The top of it is circular. I guess I could make that solid circle like this. And then, yeah, it comes down and makes a bowl-shaped type of thing, like this. Okay. So that would be where our y-axis is coming through in the middle of it. But yeah, it's shaped like that. So yeah, I agree with you. It looks bowl-shaped. Okay. Now, we're going to picture taking a slice out of this, but we want to be pretty careful in how we slice this, because if we try and make the same slice like we did last time, taking your knife and going vertically like this, slice, slice, if you tried to remove a slice that way, it would not be really easy to find the area of that. You'd be taking like this awkward kind of parabolic type thing. It would look something like this, and then it would have kind of a third dimension like that. That would be a really weird slice to try and find the cross-sectional area of, to try and find the volume of that. So that is not what we're going to go with. So not slice. We want a thing, something that we can actually find the area of more easily. So we are going to slice this the other way. We are going to take our knife, our sharp knife here, and we're going to slice this bowl-shaped object horizontally, like so. So we're going to make that type of slice. All right, because then when you pull that slice out of the object here, it's actually going to look circular. All right, like this. So that's the slice we want to work with. One slice here. Okay. So this is like the same type of shape we had just looked at. It's another disc. All right. So that's going to allow us to find the volume of this individual slice, find its cross-sectional area and its height, and bring those things together. All right. So note that this is going to have some radius and it's going to have some height associated with it. And so our delta V for this single little disc is going to be pi r squared h, all right, where the pi r squared is the cross-sectional area, and then the h is, oops, sorry, I was just trying to get that other slice out of the way there, the one that we're not using. So let me get that out of the way. Okay, not that slice. All right, the slice we want has an individual volume of pi r squared h. But notice now that the h, the thickness of this slice, is not determined by a little change in x anymore. The way that we've sliced this, it's actually determined by a little change in the y direction. So we are going to have h being delta y instead. All right. So we're going to need to keep that in mind here when we're finding the little delta V increment. Let me move that a little bit as well. All right, just so we can fit all this problem in here. Okay. So yeah, H is going to be some little change in Y. All right. We are going to need to find our radius, and then we'll have pi r squared delta Y. Okay. So, like the last problem, we can see that the radius is going to be changing here for different values of y. And when we start at the bottom here, there's a radius of 0 right at the base of the bowl right there. And then that radius is going to be increasing as we move up towards the top of the bowl. So with each slice, that radius gets larger and larger until up at the top of the bowl, we hit our largest radius of 2 units right there. Okay, so just like Brandon said on our last problem, we're going to find the radius by using the equation that's been given to us, how we use the parabola to find the radius here. We're also going to use the parabola to find the radius for these discs or these little cross sections. So this is the radius we're looking at. All right. So notice that we do find the radius based on the parabola. We would find that by looking at the x value, because we are going to be looking for the different radii in terms of y here. At each y value that we come to, there's going to be a different radius. Okay, so like we start with a radius of 0 down here. When y equals 1, we would have a radius of 1 unit. When y equals 4, we would have a radius of 2 units. So we're determining the radius by the x value, but x is really just the square root of y if we solve for x in our parabola equation right there. So that's actually what we're going to want to use, because notice how our variable here we're saying is going to be y, since we're doing things with respect to y. So we're going to need that radius equation in terms of the variable y as well. Okay, so that's what's going to go in for r right here, is the square root of y, and that's going to get squared. So we have pi square root of y squared times delta y for our little change in volume. And I'm just going to note there that everything in that full equation is in terms of y. And we needed to make that happen here. All right. So if we simplify that a little bit, you could take that square root of y and square it. It's just going to get rid of the square root. So you'd have pi y delta y. Okay, and that's what we're going to need to integrate. What are our limits going to be on this? Going from some y value to another y value.
From 4 to 0?
Yeah, good. We'd usually say 0 to 4, like small to large, but you got the right values in there. Yeah. So 0 to 4 going all the way from here to here. Cool. And so yeah, now we can set up our integral. The full volume of this, we're going to integrate from 0 to 4. And then we'll basically stick in that delta v expression. Pi y, and then instead of delta y, we're going to say dy inside the integral. All right, so once again, coming up with the integral is the hardest part, because now integrating this hopefully is not too challenging. Okay, pull that pi out if you like. Take the antiderivative of y, that would be 1/2 y squared. And then we got to plug in our limits. So we'd have 1/2 of 4 squared minus 1/2 of 0 squared. Nice, that second part just drops right out. And so we'd be taking 1/2 of 16, that would be 8, and multiplying it by pi. So we get a volume of 8 pi cubic units.